Hello and welcome back to Tech Learners. We will continue solving ordinary differential equations. In the previous lessons, we had seen the variable separable method, the linear differential equation, and homogeneous differential equation. And today, we will talk about solving exact differential equation. So let's first see what is the type of the exact differential equation. So any differential equation of this form will be called as exact differential equation whenever it can be written in the form of m dx plus n dy is equal to 0. But this will be called exact differential equation only when it satisfies this condition. So the condition is del m upon del y should be equal to del n upon del x. So this is the partial differential of m with respect to y and partial differential of n with respect to x. Let's see which equation can be termed as exact differential equation. Let's see this example. Here we can see this is y square minus x square dx plus 2xy dy. So this is in the form m dx plus n dy is equal to 0, and we can consider this term y square minus x square as it is associated with dx. This will be m for us. So this is m, and here on the right hand side this 2xy which is associated with dy, this will be n for us. So it is in this form, but whether this is exact or not, for that we have to check this condition. So let's first derivate m with respect to y. So let's partially derivate. We'll find out del m upon del y. So this is y square. This will be 2y, and minus of x square is a constant. So this will be 0. And on the right hand side, let us find out del n upon del x here. So this is del n upon del x, which we will be partially derivating this with respect to x. So here we can see x to the power 1, this will be 1, and the constant 2y will remain same. So this is 2y. And here we can see del m upon del y is 2y and del n upon del x is also 2y. So here this condition meets that del m upon del y is equal to del n upon del x in our case. So we can write that del m upon del y is equal to del n upon del x in this equation in this case. So this is the exact differential equation. Now let's see how we can solve these exact differential equations. Let's talk about the working rule. So in that case, we have to follow 3 steps. Step number 1, we will integrate m with respect to x. So this is integral m dx we have to find. In the second step, we have to find out integral of n with respect to y, but with one thing, that the terms of n, we have to take only those terms of n which do not contain x. So n, we will take terms which do not contain x. For example, let's say if we have a, let's see this example, this is n. So here we can see this is 2x cube y minus 3x square y square minus 5y to the power 4. So for integration, we will take only those terms which do not contain x. So here you can see it is containing x, we will not take this term. This term also contains x, we will not take this term. So we will only integrate minus 5y to the power 4. So this is the step number 2, and then once we have got these two solutions, we can simply write the solution, that is result of 1 plus result of 2 is equal to a constant. So let's see these examples one after the other. Let's solve this example number 1. So here we have seen that this is in the form of m dx plus n dy, and we have just checked that this is following this condition, del m upon del y is equal to del n upon del x. Just for a revision, we'll do it once again. So here in this question, we can see that this will be m and this will be n, and we need to find out. Let me write this. M is y square minus x square as it is associated with dx, and here n is 2xy. So just to check the condition, we will first identify del m upon del y. We had just done this. So del m upon del y will be 2y, and we are also calculating del n upon del x. So here del n upon del x is also 2y. So we partially differentiate this with respect to y. So here we can see the condition meets del m upon del y is equal to del n upon del x. So we conclude that this above given equation is the exact differential equation. Now we'll solve this. Just to solve this, we'll follow the three steps of the working rule, where we have to calculate in the first step integral of m dx. So let's find out integral of m dx, which is equal to integral of y square minus x square dx. So this is equal to y square x minus x cube upon 3. Integral of x square is x cube upon 3. Y square will be constant. So the integral of y square with respect to x is y square x. So this is the first step. So this is the result number 1. This is result 1. In the second step, we have to find out integral of n with respect to y, but we have to take only those terms which do not contain x. So here we can see n has only one term, and that is containing x. So we will not take this term. So we do not have to perform the integral for n anyway. So we directly jump to the third step, where we have to add result 1 and result 2. So now we'll simply write the solution. The solution is given by integral of m dx plus integral of n dy is equal to c. Here integral of m dx is y square x minus x cube upon 3 plus, so we know that we do not have anything here because we could not find any term which is free from x here. So this is equal to c, and this is our final solution for the given exact differential equation. Now let's talk about the solution of this example number 2, which is 5x to the power 4 plus 3x square y square minus 2x y cube with dx plus 2x cube y minus 3x square y square minus 5 y to the power 4 dy. So this is in the form of m dx plus n dy, where we can see this term will be m for us, and on the right hand side this term will be n for us. So let me write that m is equal to 5x to the power 4 plus 3x square y minus 2x y cube, and n will be for us 2x cube y minus 3x square y minus 5y to the power 4. Now first of all, we'll verify whether this is an exact differential equation or not. For that, we know we have to find out, we have to check the primary condition. The primary condition is del m upon del y should be equal to del n upon del x. So for that, we'll first of all find out del m upon del y. So this del m upon del y, which means partially differentiating this equation with respect to y, keeping x as constant. So here 5x to the power 4 is a constant, so will vanish. Here we have y square, so this will be 6x square y. Here minus 2xy cube, so this will be minus of 6xy square. This is the partial differential of m with respect to y. Now we'll find out the partial differential of n with respect to x. So let's see. This time we have to find out with respect to x, keeping y as constant. So this will be, this is x to the power 3. So this is 6x square y. Here x to the power 2. So this will be 6x y square, and this is only a constant, which will be a 0. We do not have any x here. So we can see this del m upon del y is 6x square y minus 6xy square, and del n upon del x is also 6x square y minus 6xy square. So from these two, we can conclude that del m upon del y is equal to del n upon del x in our case. So we can see that this equation, the given equation, is the exact differential equation. Now you'll just write the solution. For that, we'll perform step number 1, where we have to integrate. The solution is given by integral of m dx plus integral of n dy, where n is free from, we must write it is free from x, is equal to c. So let's find out integral of m. This is integral of 5x to the power 4 plus 3x square y square minus 2xy cube with respect to dx. This will be, here we can see integral with respect to x. So this is 5x, 4 will be 5x to the power 5 upon 5. So here this is 5x to the power 5 upon 5. So we cancel out these 5. So this becomes x to the power 5. The first term comes to be x to the power 5. Then in the second term, this is x square. So x square, the integral of x square is x cube upon 3. So here we have 3 y square. So this 3 and 3 will be cancelled. So we left with x cube y square. So this is x cube y square. In the third term, this is x to the power 1. So this will be 2x square upon 2 dot y cube. So here we can cancel this 2 and 2. So we are left with x square y cube. So this is minus x square y cube. So this is the integral m dx. So now we'll solve integral of n dy and we'll take only those terms of n which are free from x. So here we can see this is 2x cube y, it's not free from x. Minus 3x square y square, it is also not free from x. And here minus 5y to the power 4 which is free from x. So we'll only consider minus 5y to the power 4 and we'll integrate this with respect to y. So the solution for this will be y to the power 4, this is y to the power 5 upon 5. So this will be minus y to the power 5 upon 5, 5 and 5 will be cancelled. We are left with minus y to the power 5. So the result of this is minus y to the power 5. So we have got the integral of n dy and now we simply write the solution. The solution is written in this form. So we'll simply write first integral of m dx. This is x to the power 5 plus x cube y square minus x square y cube. So this is integral m dx plus integral n dy which is minus of y to the power 5. We'll write minus y to the power 5 and this is equal to, you have to write a constant which is c. So this is the solution of this given exact differential. Here we can see this is in the form m dx plus n dy where this is m and this will be n. So let me write, this is m is 2xy cos of x square minus 2xy plus 1, this is m, and n is sine of x square minus x square plus 3. So we need to identify whether this is an exact differential equation or not by checking the condition. The condition is del m upon del y should be equal to del n upon del x. For that we'll find out first del m upon del y, which means we have to partially differentiate this equation with respect to y. So let's do it. Here the first term we have only y to the power 1, so this will be 1. So 2x cos of x square will remain. So this is 2x cos of x square. Then in minus 2xy we have y to the power 1 again, so this will be only minus of 2x and plus 1, this is a constant, will be 0. So this is del m upon del y. Now we'll identify del n upon del x. So now we have to partially differentiate this with respect to x. So first of all, this is sine of x square. We'll do it with the chain rule. So first of all, sine of x square will be cos of x square and then we'll multiply this with the differential of x square. So the differential of x square is 2x. So we'll add 2x. This is cos of, so the differential of sine of x square comes to be 2x cos of x square. Now the next term minus of x square will be minus of 2x and plus 3 is a constant, so this is 0. Now we can see del m upon del y is 2x cos of x square minus 2x and del n upon del x is also 2 of x cos of x square minus of 2x. So we can conclude that here del m upon del y is equal to del n upon del x. So this is the exact differential equation. Now we'll solve this. So integral of m with respect to x would be integral of 2xy cos of x square dx minus integral 2xy with dx plus integral 1 dx. So here we can solve this with the help of the substitution method. In this we will substitute x square by t. So we'll first solving this integral by substitution method. So let me write it here. We'll substitute x square as t, which will be 2x dx is equal to dt. So here we can see this x square will become t and this 2x dx will become dt. So this will be left with 2x dx will be dt, y will remain same, that this is a constant, and cos of x square will be cos of t. So here we can see this is the integral of cos t actually, because y is constant. So we can keep y outside and then we'll perform the integral of cos t, which is sin t. So this will be y sin t, and then we'll replace this t back. So this will be y sin of x square. So the integral of 2xy cos x square dx comes to be y sin of x square. So let me replace this back here. This is y sin x square. Now the next is minus of 2xy, where minus of 2y is constant. The integral of x will be x square upon 2. We'll cancel 2 and 2. So this will be, we can see minus 2y and x square by 2, where we can cancel out this 2 and 2. So this is remain minus y x square. So let me rewrite this as minus y x square. And lastly, this will be plus x as 1. This is a constant, so we'll have one integral as plus of x. So this is integral m dx. In the second step, we have to find out integral of n dy, but we have to take only those terms which are free from x. So here we can see in this sine of x square, it's not free from x. Minus of x square, it is also not free from x, but plus 3, yes, this is free from x. So we do not have any x here, so we take only this term. So in the second step, in the term of integral n dy, this will be only integral 3 dy. As we can see, only this term is free from x. So the integral of a constant will be 3y. So this is 3y. And here hence we'll write the solution. So the solution is written as integral m dx plus integral n dy is equal to c, which will be y sine of x square minus y x square plus x, and then this is plus 3y is a constant c. So this is the solution for the given exact differential equations. In the upcoming lectures, we will be talking about the reducible forms of these differential equations, and we will be talking about higher order differential equations and higher degree differential equations.